Now we're ready to start interpreting the intercept and coefficients in a logistic regression model. But first, let's just refresh on how to interpret the odds ratio. Remember that when the log odds ratio is greater than 0, it means that the odds ratio is greater than 1. So that means the probability of success is bigger than the probability of failure. But when we have negative log odds ratios, a log odds ratio of less than 0, it means that the odds ratio, p over 1 minus p, is less than 1, which means that the probability of success is less than the probability of failure. This is going to become important as we try to understand how the intercept and coefficients can be translated into a meaning for our business problem. So looking back to our model, we remember we would label P as the probability of today being an options expiration day, and it depends on market volume and volatility according to our model. The intercept is a negative 4.89, and we can start to interpret that in a similar way to the way we interpret an intercept in a linear regression model by plugging in a 0 for market volume and a 0 for volatility. When market volume and VIX are 0, then the log of the ratios of probability of having an options expiration day and not having an options expiration day is equal to negative 4.89. So that sentence begins in the old-fashioned way, plug in zeros, but it ends with this thing that the log odds ratio is equal to negative 4.89, and we don't yet know how to make an interpretation of that statement. So what we're going to do is look at that mathematical statement and try to solve for P. So you'll never have to do this calculation, but I want you to see what's happening under the surface because you will have to do the last bit of calculation at the end. So in order to isolate P and solve for P as a number, we have to eliminate that logarithm. P is a single number. It's a probability. It's a number between 0 and 1. Not going to be 0 and it's not going to be 1. And there's only one unknown in this equation, so we can definitely figure out the value of P. The first thing we need to do to eliminate the logarithm is exponentiate both sides of the equation. So the opposite of the natural logarithm is the exponential function e, because the logarithm has a base of e. Once we've done that, we can solve using algebra. So let's see how it would work. The first step would be to exponentiate both sides, and we would have e to the log odds ratio equals e to the negative 4.89. The next step would be to write it in a simpler way. The e and the log function cancel one another out, so we have something much simpler now. P over 1 minus p equals e to the negative 4.89. Now, e is a number. It's 2.718 something, and there are many, infinitely many decimal places after, but it's still a number. So a number, imagine that it's 2 raised to the power of another number is just a number. So the right-hand side of this new equation is just a number. And we have p over 1 minus p equals some number. We can multiply both sides by 1 minus p in order to get the 1 minus p out from underneath p on the left-hand side. So we have p equals e to the negative 4.89 times 1 minus p. We'll multiply that out using the distributive property, and we'll have p equals e to the negative 4.89 minus p times e to the negative 4.89 power. Now we can move both p's to the same side because we're trying to isolate p in one location. And then we'll extract p from the statement. So we'll have p times the quantity 1 plus e to the negative 4.89 equals e to the negative 4.89. Once we get here, we can divide both sides by 1 plus e to the negative 4.89. And we have an equation for p. This is great news. But now we need to know what is P equal to? What is that number? We know it will be a number, but we can't say what that number will be because our brains are human brains and not computers. So we'll need to use R to find that number. Here we are in R to find out what that number really is. So we know that it's e to the negative 4.89, and the way that we type e into R is the exponential function. So exp parentheses negative 4.89. And we need to divide by 1 plus e to the negative 4.89. So we'll need parentheses because if we forget them, we won't actually be executing the right statement. So parentheses 1 plus exp negative 4.89. And when I press enter, whoops, that doesn't look good. Negative 4.89. I have two sets of parentheses in the denominator because exp is a function. My answer is 0.007465273. So let's round that to 0.0075. So 0.0075 is the answer to our problem. So when we have that intercept, when market volume is 0 and volatility is 0, which means there was no trading and there was no price action, no prices moving today, we had the log of the odds ratio for an options expiration day is equal to negative 4.89. And that means it was a very, very small probability P. So the probability of success, or the probability that it's an options expiration date, is very small. So with a negative 4.89 intercept, we're really talking about a day where there's no market volume and no volatility. And on such a day, the odds of an options expiration is really small. So what we're saying is when the log odds ratio is very negative, like a negative 4.89, P is going to be very small. If that intercept was a negative 10, P would be even smaller. Our intuition says yes, it makes sense that with all else held constant, most days are not options expiration days. So on a day when there was no market volume and low volatility, yes, I think it's reasonable that we have a very small probability of being an options expiration day.